is Shai from Waterloo.
Yeah, right. Okay. Yeah, so this is going to be very, very different than the last talk. I mean, it is kind of, I want to talk about the 20 years of theory chasing practice, and it's a very subjective view. I'm talking about my own experience with my limited knowledge of what's happening in the world. So yeah, I mean, basically we know it. I mean, what is domain adaptation? The data at training time is very different than the data at test time, and we want to, the goal is to adapt existing model to the data at test time without having to retrain from scratch. And there are lots of kind of more specific tasks under this umbrella of adapting to training data to a new environment. And I will focus on domain adaptation, and I will focus on binary classification, but I think that most of the things that I say are also as well applicable to these other types of tasks. So let me start by just telling you about my own experience with domain adaptation, and it had to do with closing the gap between theory and practice. So my first encounter was in a Snowbird in 2005. You know, we used to have meetings in Snowbird in Utah, and that was before AI Stats. And so these guys came to me, I didn't know them before, John Blitzer and Fernando Pereira, and said, we have an algorithm for NLP that works very nicely in practice, but we have no idea why it is working. Can you help us figure out why it is working? So the algorithm was doing, it is a successful algorithm for adapting part of speech tagging. So they wanted to tag part of speech, they train it on Wall Street Journal text, and then they wanted to apply it to do part of speech tagging in some medical documents. And they had an algorithm that worked surprisingly well. It surprised them how well it worked, and they wanted to come up with the explanation why it works so well. So I will just tell you one thing about this, the algorithm. So what was the idea of the algorithm? It was an NLP algorithm. So they say, choose a set of pivot words. So determiners, prepositions, connectors, frequently occurring words. Those kind of pivot words, they occur with similar frequency in Wall Street Journal documents and in medical documents. And then you represent every word by the window around it of the pivot words around it. So we no longer look at the word, but we just look at the distribution of pivot words in a window of, say, 5 words to the left or to the right of this word. And then this is the representation of the data. And then they train the linear separator on the images of this kind of representation of the data, the part of speech tagging from the Wall Street Journal, and applied it to the medical data. So if you wanted to know if a word is I don't know what part of speech, it's a verb or an adjective or what it refers to, they just try to train it based on its neighboring pivotal words. And based on that predict, and that kind of prediction carried over from the domain of the journalism to Wall Street Journal to the domain of medical data. So that's the algorithm that they had. It worked, at that time it was a nice performance, and they wanted to come up with a model that explains why it does it. So we came up with the following paradigm. The funny thing is that, where is Kamalika is here? It's exactly the same principle that so I'm kind of stealing your ideas backwards to 2005. So the idea was that what they actually did, that they embedded the original attribute space, both the source and target, into some feature space that had 2 important properties. The feature space was representing every word by the frequency of pivotal words in its neighborhood. And the 2 important properties were that under this embedding, the 2 tasks had similar distribution. So the distribution of words among their neighbors, pivotal words, looked the same on the Wall Street Journal and on the medical data. And this representation was rich enough to allow to predict the part of speech tagging. So we said, okay, so this is what you need. You need to embed your data in a feature space such that you have these two properties. And now when you come to predict time, you just train a predictor on your source data, because on your source data, you have labels, and you take your test point, you embed it in this space, and use your predictor that you trained on the source data. So that's basically was the idea. We formalized it. What?
Like the inputs look similar, but that also the input-output correspondence is similar.
Right. I'll give an analysis of this in a minute, but the main one point to notice here is they trained it without any labels on the target domain, only labeled on the source domain. So this is unlabeled domain adaptation. So under these assumptions, we could prove this kind of general uniform convergence bound. So what does this uniform convergence bound? So say that we have here Q and P. P is the source distribution and Q is the target distribution. And these are distributions over instances and their labels. And the loss of any H in the class, their class was the class of linear predictors. So the loss of any H in the class on the target is bounded by the loss on the source plus these two terms. So the conclusion from that, these two terms are independent of the specific word that you are trying to predict the label for. So the conclusion is just try to minimize the loss on the source. And these are kind of constants once you fix your embedding and the source and the target. So the idea is like, if you have such an embedding, you don't need any adaptation. You just train on the source and it will behave nicely on the target. So what are these two terms? So the two terms, one of them, this term is just measuring the discrepancy between the marginal distributions. So the distributions of the data without any labels, you need some measure of the marginal discrepancy between the two distributions. This is after the embedding, and lambda is measuring, that's I guess what Zach was asking, the discrepancy between the labeling rules. So in some sense, this is the two components that you need. You need to know by how much your marginal shifted, and that's the D term, and by how much the labeling rule is different. So that was the kind of the basic conclusion of this research. So we proved this result, and that kind of started a real long chain of research. So right after that, the principle is that you have to measure the drift of the marginal, and you have to measure the change of the distribution. And so it started a long chain of research. And what I want to say is that at that point, it felt like a very good match. I mean, the theme that I want to emphasize is the gap between theory and practice. And at this point, it looked like a very good match between theory and practice. They came with a practical algorithm. We came up with a theoretical model, and everything fitted very nicely. So the theoretical contribution was that we are able to explain what is a good representation. And once you have a good representation, you need no adaptation. But there was a very good match between the theory and the practice at the time. The problem is that the practice at the time, that the embedding was handcrafted. So that's very different than the practice today. So the embedding was handcrafted, and we made it as assumption, just like you did. We assumed that you have such wonderful embedding of the data. So how did this line of research progress? So the next thing that happened is that many follow work tried to refine and generalize those two measures. So generalize the measures of the discrepancy between the distribution of the source and the target. So I think the first generalization was by Shai Mansour and Mori, and then a long list that the last brick in this wall is what Samori and Steve presented a couple of days ago. And so this is one kind of line of research. Then another question that came up, and it's a very important question, is this is assuming that we did not, I mean, what is happening? How do you incorporate data that you have on the target? Because if you look back at what we had here is just saying, just train on the source, just train on P, try to minimize the loss on P. You don't have to worry about the target. But in many situations, you do have data from the target and you want to utilize it. So the next question here was kind of, how do you incorporate more target training data when you do have target training data? And for that, I mean, you can ask, how do I get data from the target? It could be randomly generated labels examples, maybe you have just a few of them. It could also be the result of active learning on the target. And so that was kind of one line of research. The other one was the direction of how to incorporate data from the source and data from the target. And the last one is, how do we find such a good representation? Because in that case that we studied, that was based on human knowledge, on human crafted features. And I mean, nowadays we are doing applications where we do not have this type of human knowledge. So these are the three lines of research that grew out, follow this work. So let me talk a little bit about the discrepancy. So the first line, the first follow-up was by Shai and Meir and Afshin, and they generalized it to other learning tasks like multi-class learning, regression, novelty detection, and various notion of losses, because we just looked at the binary loss of a binary prediction, 0-1 loss. And the last brick in this line is the work of Steve and Samori, that they kind of say in a high level, what do you need from this discrepancy measure to satisfy? It should satisfy something like that for every hypothesis or for every good hypothesis, the loss of the source is not much smaller than the loss on the target. There's no much gap. So they kind of generalized what you need from this notion of discrepancy. And then with each of those generalization came performance guarantees that based on this type of discrepancy. So there are performance guarantees based on discrepancy, like the DH distance that we were using, performance guarantees based on discrepancy that's measured by Wasserstein distance. By all kind of distances between the two distributions, you get different type of guarantees. And the last thing that we need here is kind of notion of how can we evaluate the relatedness between the source and the target, and that still is a very difficult problem. I think that even in your case, it's difficult to say, if I give you two distributions, to evaluate how related they are. Okay, so I'm saying that the main challenge that is still open, in my view, is detecting and measuring the source target discrepancies. Are they really different? How much are they different? And we will see that this plays an important role when we try to implement algorithms. So, so this is the challenge of change detection. And in the change detection, there is a very basic lesson that somehow I see lots of research kind of ignoring it or happily forgetting it. There is a no free lunch result. You cannot, if I give you the two sample problem, if I give you samples from two samples and ask you, did they come from the same distribution or did they come from two distributions that are pretty far, there is no way you can reliably answer it from finite data, from data whose size is independent of the domain. So if I want to know, was there a change in my data, not to mention measure this change, we cannot do it without prior assumptions. This is kind of provably too difficult. There is no And in some way, it says there's no way to distinguish between in-distribution from out-of-distribution data. Today, it is very kind of more fashionable to talk about out-of-distribution learning or extrapolation learning rather than domain adaptation. And the main thing to remember, if I give you a sample and then I give you a point and ask you, does the point come from the same sample, from the same distribution that generated the sample? Even if I give you a whole sample, there is no way that you can reliably answer this question, even under assumptions like that the support of the first distribution is disjoint from the support of the other distribution. We can very easily show no free lunch results for this. So this is really an open challenge, and it is only solved in practice without guarantees. Okay, so yes.
Hand wavy proof for why there's no free lunch there?
Right. So here's my hand wavy. Here's my hand wavy proof. I really love to give this example. So assume that I'm running a lottery, and I'm if you manage to guess all the 6 numbers or 10 numbers, then you get $1 billion, whatever, right? So, but I am not happy with my income and I want to improve it. So what do? I run my lottery 1,000 times and I collect all the results that I got. And now from now on, instead of running the lottery, I will just randomly pick from the 1,000 examples that I have. That's a big cheating because I can go and just guess, buy 1,000 tickets, guess those 1,000 results, and I will win every single week. How long will it take you to detect that I'm cheating? So when I'm picking randomly from these 1,000 examples, it looks exactly like I was picking from the real distribution. And this is very, the distance between those distributions is huge. And unless you see repetitions of my guesses, you cannot tell that I'm cheating. So that's basically the proof of the no free lunch. And so it could be just that, you know, those 2 distributions look like this. You have no way of knowing it. Okay. So I think that's a big problem here, and that detecting when there was a change and measuring the change between the 2 distributions. Okay, so the next point that we need to address is how do we incorporate target knowledge? Because in the original paper we didn't have to worry about it. There was no labeling on a target. In reality, in many cases, you do have labeling on a target. You want to incorporate these 2 sources. So what we suggested in 2010 in the extension of the paper is some kind of a weighted empirical loss. You have empirical loss of a hypothesis that you train on the source. You have loss of a hypothesis that you train on the target, and you somehow want to pick a hypothesis that has minimal weighted empirical loss. And the question is, how do you weight this? How do you weigh these 2 losses? Steve and Samori offered a different way of incorporating those 2 because they create confidence sets, and they want to say search over the intersection of these 2 confidence sets, but it's the same challenge. The challenge is you have data from the source, you have data from the target. You want to utilize both of the sources, and what's the best way to do it? And the point is that no matter how you do it, this heavily depends on quantifying the relative discrepancy. Because if the 2 distributions are the same, then you can just merge all the samples together. And if they are very different, then you have to be very careful about how you mix it. So it really depends on estimating the relative, quantifying the relative discrepancy, which, as I said before, it's a big challenge. And if you think about it a little bit more, this is at a high level. The problem we are having here is actually a very fundamental issue, which is balancing the utilization of prior knowledge versus posterior evidence. Because your prior knowledge is the source data. You have the source domain, and you know a lot about the source domain, and that's kind of a prior knowledge. including your assumption of how related are the domains. Then you start seeing data from the target domain, and it's the basic question of how do we utilize combined prior knowledge from posterior evidence. And the other question that comes in, which is also a very fundamental question, is confidence or uncertainty evaluation. Because when I use the source and I want to predict, or I use the target and I want to predict, I want to know how certain I am. It depends on the sizes of the sample. I mean, in your confidence sets, you explicitly go after this notion of how confident I am of my prediction. So I think it raises two very basic questions in machine learning. One of them is the prior versus posterior, and the other one is estimating your confidence. Because if you have two sources, you need to know which of them is more confident on your current prediction. Okay, so let me go to the next step. So we said one thing was how do we measure discrepancy, and there's a lot of work on this. The second topic that we wanted to understand is how to combine the data from the source from the data from the target. That's what I talked about now. The third challenge is how do we find useful representations? We could describe what we want from a useful representation, but how do we find it? And that's a really big challenge. And this is where we start splitting between theory and practice. And I think we actually split into three domains. There is the theory, there is academic research, which, you know, I will not call it theory and Zach will not call it practice. It is sitting in between. And there is the practice, what really happens in the industry. So some kind of approaches for getting a good representation is the contrastive learning, where you take examples, you take those photo of examples. I will not get into describing it. That's the work of Teng-Yu Ma and the whole group around him. There is causality and feature invariance, which I do want to mention because we just heard talks about it yesterday. So I feel that, of course, if we understand causality, then life will be wonderful. We will know what is the causes of everything, what is the cause, what is not a cause. You will be able to be fair, interpretable, do everything fantastically, but we don't understand causality. And I think that the use of the term causality is somewhat misleading because there is a big gap between the semantics in real life of saying that A is a cause of B and the technical use when you use it in machine learning when you use causality-based tools. So that's a comment to you, right? I prefer to use the notion of invariance. We want to detect which features are invariant between the source of the target or between my data collecting to my testing. And invariance is also difficult because I think that there is no clear distinction between invariant and spurious features. I don't remember which talk it was that was talking about spurious shortcuts and you again, okay? So there is no clear definition. I mean, if I detect a cow by the black and white stains on its skin, is it spurious or is it really a feature of a cow? Because there are also cows without it, but it is a feature that may help me detect cows. So I think there is an issue of clear definitions here, and it's not as clean cut as presented. And there's a lot of work that says, you know, separate the invariant features from the invariant features, learn the invariant features, throw away the background, all the invariant features. It is a very naive assumption that there is such a distinction and that you know what the distinction is. And that's a very strong assumption. And yeah, we talk about the search for useful representation. I'm saying this is kind of going from theory to academic research. There's a lot of academic research along these lines, but I wouldn't call it pure theory because we cannot prove any guarantees. Only on a very strong assumption that we understand what is invariant, what is causality, and it goes all the way to foundational models that we just heard about, and they are scary, and maybe it's a new domain completely, but it is very far from what we can understand with theory. So If we go into academic research towards practical development, I would say, again, I like to divide everything into three parts. So here there is the approach that views the switchers as natural science approach. So what I would call anthropological studies. That's what we heard from Jacob this morning. I mean, I did this prompt to the LLM, that's what I got. Then I gave another prompt, that's what I got. It is really anthropological studies. I go to this village in Africa and I record what I'm seeing. My village in Africa now is the LLM model. Another approach is that you kind of design experiments on crafted data. So that's when you take an image and you blur it and you try to learn to do domain adaptation from the non-blurred images to the blurred images. Or you take the colors and make it black and white. You craft your data. So that's kind of experimental work, which we see a lot in physics, in biology, and so on. But it's kind of natural science. We see the world of Teng Yuma. And there is developing practical heuristics that which had a lot of few-shot learning and heuristics that you can see that they work on your test data, but it's very difficult to completely justify. I hope I'm not. Okay, and finally, at the end of this line, there are tools that actually work in applications. So Zach claims that his tools do work in applications, and I have no clue how they're doing it, but what I feel is that the gap between our theoretical understanding and what is happening in practice is much bigger now than it was 20 years ago when we started to work on those issues. And it's not, I think the theoretical research developed much more slowly than what was happening, the development that we were seeing in practice. Okay, so let me just conclude with some remarks on where we are. So I think that in terms of theory, there is no hope for a general task-independent theory of domain adaptation. I think that impactful tools, if you want to understand it, should really rely on a lot of domain knowledge. And domain knowledge is different for every domain. I mean, you see the research, you see that we have a lot about images and NLP. As we go along here, we have less and less successful applications. And my feeling is that you want to address some domain, you have to collect understanding of the domain. I have a friend who had a startup that was trying to predict for architecture pricing of blueberries. According to images, you take images of blueberries and you want to predict the price that it will make in the market. And the domain adaptation here is that you train it, say, on fresh blueberries, but then you have blueberries that were shipped from Mexico or from whatever, and they are 2 days old, and now you have to adapt. And it's a very different story than adaptation of a cow from the grass to the water. So my feeling is that for whatever applications you have in mind, you have to collect domain knowledge and even develop your theory around this domain knowledge. So I think that's all I wanted to tell you today, and I'll be happy to discuss it in the panel afterwards. Yes.
Maybe there are large categories of shift for which you could.
I mean, we saw it. You were trying to say there are different categories. There is the balancing difference. There is the background difference. I feel that this is very theoretical, theoretical in the sense of not really reflecting reality. Yes. Yeah. No.
Thanks for your talk. I enjoyed that a lot. On your last point here, is it really the separation of images and text and diagnoses, or is it that the tools really need to be tied to the kind of task that you want to do with these things?
Definitely it had to be tied to the task that you want to do with it. I think that part of our success in images in NLP is that we understand it so well. I mean, we do it all the time. We speak, we look, we analyze what we see. So yeah, it has to do with the task. I mean, I have right. I mean, I can tell you all kind of stories, but I have a nephew that was trying to get a job as a machine learning person. He never studied machine learning, and they gave him a task of sentiment analysis of reviews of hotels. And he figured out that the best sentiment analysis is say, if the review is long, it's negative, and if the review is short, it's positive, and it worked so well that he got the job. But I think that when you take this and try to adapt it to reviews of movies, it will no longer work. Although it's kind of sentiment analysis of NLP in both cases. Yes, Sasha. I mean, after they called me Ben, I can do.
You said that 20 years ago, the gap between theory and practice was much smaller than it is now. Do you think that the gap was smaller, or we just didn't perceive the gap as much?
So I think the gap was smaller in the sense that practice was much more transparent. Like, and when they came out with the embedding, they knew exactly what they were doing. But when you embed the data through a large language model, and you look at the top layer, and that's your representation of the data, you don't really in control of the representation. So when it was manually done, it was much easier to get an insight or understanding of what is happening. So I think that's what I meant by that.
Well, what about things like boosting? Did people really understand what boosting actually did? What does it mean?
That's ask Peter.
That's a no.
What?
I'd side with Misha and say,
Right, yeah. Yeah, so there were things that we do not understand. I'm talking about domain adaptation. Yes.
So if we compare your result and
I don't know.
if we compare your result with the Samuel and Steve's result, so first you introduce a measure and you estimate the measure, and your transcendental algorithm is based on the estimation of the measure.
Right.
However, they propose an algorithm that without prior knowledge of the distance between source and target, we can achieve the optimal rate. So the question is that, do we really need to first estimate the distance between source and target and then perform an algorithm, or without?
I think that without estimating the distance, you will not be able to give guarantees for the performance on your target. Because one of the advantages of the measure that we suggested in that paper is that we could see that you can estimate, we could show that you can estimate this distance from finite data. You can give sample size, uniform convergence types of estimating this distance. And the distance plays a crucial role, especially when you also have target labels and you want to somehow trade off the data from the target and the data from the source. So I think it's an important question, and I don't see how Steve and Samori can estimate their notion of distance, but.
I mean, I can take it offline. Yeah.
Okay.
I'll make the points during the
discussion after. Okay. Yes, Dean.
So, are there any work that tries to, so I was trying, if I understand correctly, the source and distribution both kind of IIT data?
Right.
So what if my source is a time series?
Right. No, I think it's a very interesting question, and I did not think about it seriously, so I cannot give you a good answer. But I think it's a very good question. We still make here the simplistic assumption that the source is IID and the target is IID, and the only change is kind of it was a kind of a phase transition between going from the source from the data, from the target. And with temporal data, it's a different story. Yeah. Could be a different story. Yes, sir.
I mean, it's like one line of, I don't want to say attack, let's say attack, why not? You're a competitive fellow. on the characterization would be like, well, were theory and practice as close as you make out 20 years ago, or are they actually quite further? So like, you know, I think it's a nice like description, characterization of like what might have gone on in this particular model that Fernando and his buddy were working on at the time. At the same time, was it ever the case that like the practitioner was out there actively seeking the, you know, taking the data from the new domain and actively constructing the representation in such a way to make this happen, or is it more like you're saying, hey, here's a conservative upper bound. This is, hey, if these three
No,
things
right.
are, you know,
But
well
I think
enforced,
that when we
everything
say,
within
when we
the
talk,
marketplace
yeah.
was the same, then nothing's different and whatever, but
I-
reality was if we're applying models that the
Yeah,
data
I
was
think when we
bouncing,
talk
like,
about the
sometimes it
gap,
worked, sometimes it didn't, and
I think when we talk about the gap, there are different meaning to it. One meaning which I kind of refer to is, do we feel that we understand what happened in practice? It is very different than saying, is my theory being applied and impactful in the real world? And I don't know what's happening in the real world, so I cannot tell you, but it's different notions of gap, yeah.
So along those lines that, so maybe not the real world in the companies, but in academic research, the kind of setup that you have inspired representation learning setups, right? So the idea of trying to bring the source and the target
Right.
closer together as a one of the terms in your representation learning is popular.
Yeah,
So
it became
whether that's
popular.
directly from theory or not, it's still
Yeah,
brings the two closer together to some degree.
yeah, I think we're closer to academic research than to applications the way Zach
a
uses it.
popular line of work, but it doesn't actually work, right? Like nobody actually uses something in adversarial learning in any real world problem, but also the academic papers in that line also don't quite work, right? And that's a whole separate line, but they're almost all cases of like cheating and looking at holdout labels in order to choose
Citing.
fraud.
Yeah.
Okay, I think that's it for now. So thanks again to Shai.